Okay, so let me explain to you how we use electronegativity in identifying the electronegativity and whether bonds are polar or nonpolar, and I'll explain that to you. The first thing you need to know is what is the definition of electronegativity? It is the tendency of an atom to attract electrons to itself. So basically, it's the attraction of electrons. Now, if there is, for example, group 1A, those metals, they have extremely low electronegativity, and you can see that over here. And therefore, sometimes they are called electropositive, and that's because they don't even pull electrons, they just give their electrons. And then electronegativity will decrease as you move down a family because the atomic radius increases as you move down a family. And therefore, and my drawings are just fantastic, but and therefore the electronegativity will decrease because it's easier to pull those electrons away. Then, if we're looking at a period, the electronegativity increases, and this is going back, of course, to our periodic trends web quest, because there's an increase in the nuclear charge and decreasing atomic radius. And so if you look how the numbers increase, we go from 1 to 1.5 to 2.0 and so on and so forth. And for the elements that we see the most, this is a nice little relative electronegativity list. And I want you to note that fluorine has the greatest electronegativity because if you think about it, it's the farthest towards the top, so it's the smallest in a family, and it's the farthest toward the right, so it's the smallest in the period, and therefore it has the greatest electronegativity. And then you can just kind of look, the numbers kind of tell you, the order. Now, the reason we're doing this is because covalent bonds actually come in two types. And if the electronegativities are the same, we call that a nonpolar covalent bond. And that is because the electrons will be shared equally because they have an equal pull. When atoms of similar but different electronegativities, and usually that is less than about 1.7 difference, the more electronegative atom has a greater share of the electrons, and therefore that the electronegative atom has a partial negative charge, and we call that kind of bond a polar covalent bond. So there are two types, and so now instead of just ionic and covalent, we have ionic and polar covalent and non-polar covalent. Okay, those are the different types of bonds. So what you have to remember, of course, is that nonmetals are more electronegative than metals. And when there is extreme difference in electronegativity, like greater than 1.7, what results is an ionic bond, and that's because there will be a movement of those electrons. Now, here are some examples, and you can look at the picture of the periodic table with the negativities on it that you received in class. Here we have nonpolar covalent bonds. First example, if there are identical nonmetallic atoms, they have identical electronegativities, and therefore it is a nonpolar covalent bond because they're equal to each other. If there are different atoms with the same electronegativity, there will be equal sharing and so it's a non-polar covalent bond. So this is two situations in which you can have a non-polar covalent bond. If they're the same element, or if they're different elements with the same electronegativity. Polar covalent bonds. In polar covalent bonds, what happens is if you look at the numbers, and you can look at the table, OH has electronegativity of, or excuse me, O has an electronegativity of 3.5, and H has an electronegativity of 2.1. So 3.5 minus 2.1 is 1.4. And if we go back up to this area up here, where we were reading above, if it is less than 1.7, then what happens is a polar covalent bond results, and that is the case here. So oxygen is more electronegative, so it will have a greater share. And what we do is say that it is partially negative. And I'm going to enlarge this. It is this letter and a negative sign. Okay, that's a Greek letter. And then hydrogen is slightly positive. Okay. When this happens, that means that the bond has two poles, two ends, and this is called a dipole. Okay, and so you can do different things here. You can have the slightly positive and slightly negative signs, and that's what's being shown in this one. Or sometimes what will happen is an arrow will be drawn with a little plus on the side that is slightly positive to show that the arrowhead points to the most electronegative atom. And then we know this already, the ionic bonds, and you can look at what the elements are for this. This is not as hard as distinguishing between polar and nonpolar, but for example, sodium and fluorine, sodium is 0.9, fluorine is 4.0, difference is 3.1, it's greater than 1.7, so the result is an ionic bond. Okay, so this is the assignment again, and we've already done number 1, and we've done number 4. And so now I would like us to look at number 2 and right here. And what you're going to do is you're going to actually use these numbers that are in this periodic table down here, and you are going to look at the differences in electronegativities between the central atom and the atoms bonded to it, and you are going to record those differences, okay? All it is little addition and subtraction and reading the periodic, and reading this table here. So let's start. Let's start by looking at methane, which is CH4, and we already looked at this. We drew it in our Lewis dot structure. So we've got our hydrogen here, which is 2.1, and our carbon is 2.5. And so the difference between them is 0.4. All right, so we said that if there is a difference in electronegativity of less than 1.4, or I don't know why I wrote 4, I think it's because it's 0.4, 1.7, then that type of bond, and now I'm talking about the bond, not the whole molecule, but just that bond, the difference is less than 1.7, therefore it is a polar covalent bond. And so we've got our slightly positives and our slightly negative in the middle, and that's nonpolar. Now, hold off drawing all of these symbols for now. I just want you to do the calculating of these numbers here to start. Okay, here's another one. We have nitrogen, which is 3.0. And fluorine, which is 4.0. And the difference between them is 1.0. And that is less than 1.7. Okay, so those are all polar covalent bonds. Now, which direction is which? In this case, we've got our fluorine is pulling the electrons, okay, because it has a higher or greater electronegativity. So it looks like that. Notice, by the way, we are not doing this at all for ionic. This is purely covalent. In this one here, we've got nitrogen, which is 3.0, and we've got hydrogen, which is 2.1, and the difference between those is 1.1, and that is less than 1.7, and therefore there is a polar bond. And so the pull of electrons is towards the nitrogen, and so it would be kind of like this. And then, of course, good old water. And this is just so important for biology, for chemistry later on when we talk about solutions and that sort of thing. I told you that, this is the structure, and that's how you should know it. But we're not talking yet about the shapes. So really the most important thing for me right now is that you understand the electronegativity. So oxygen is 3.5 and hydrogen is 2.1. And so there is a difference of 1.4, correct? Maybe my math is not correct, but I think it is. And that is less than 1.7. And therefore it is a polar covalent bond. And this is the classic example of a polar covalent bond. Water's polarity makes it a very versatile solvent. All of life takes place in water, and therefore it is something you should just know. Learn that for your science classes. Last one I'll do is the HCN again. And carbon is our central atom. And so we've got carbon is 2.5. And nitrogen is 3.0, which is a difference of 1.5. And we have hydrogen is 2.1. And carbon is 2.5, okay? And so the difference between those two is just 0.4, okay? Now, again, less than 1.7 equals polar covalent bond, all right? So if we look at this, again, we've got the positive on the hydrogen side that carbon is pulling. Now, in these two, the 1.5 is really, really close. They're very close together. But because nitrogen has a little bit higher number, you have the pull of electrons even further. But you almost can't even put the positive because this carbon is already pulling the electrons from the hydrogen.